Good afternoon, all of you. This is the third day of online machine learning, deep learning, and its application program. Before that, we have covered on the first day to just give the understanding about remote sensing, platform and sensors, radiometric and geometric corrections, then basic understanding of image. Later on, we have also covered on as in basic classifier to machine learning, a journey we have reached till date, and then a Python for machine and deep learning models. So today, myself, Anil Kumar, is starting the fourth lecture in this series on methods in machine learning, supervised, unsupervised, and reinforced. Basically, how the algorithm works, what is the prior knowledge it is required. Based on that, algorithm is getting trained and then starts working for classification, clustering, detection, prediction, and so forth. It is just like a human being or any creature when it comes in this physical world. That person is not trained, right? That person is in the form of a baby, not trained. He does or she does irregular official courses, unofficial courses to do learning, to acquire knowledge. And based on that knowledge, they start working independently and tackling the task. And they also use very smartly the intelligence on the spot, taking decisions. So same way here, up to certain limit, these methods, how they get trained to handle a task which can be related to classification, that is supervised, or grouping the pixels, rather we can say in a simple form, or we can say clustering. Without labels, we are trying to group, or this for detection, just to detect what that object is, it is ship or car, plus regression to predict tomorrow rain will occur or not. So all these things, we'll see how this happens. So here, if you see type of machine learning methods, specifically the learning method or training method, how to train a model. So there are basically four methods we can see. Two are very common. One is supervised method and second is unsupervised method. Third is semi-supervised, and fourth is reinforced method. Here, if you see the first one, or overall in these four methods, what is required? We require a training data. Training, we can say, or we can say samples which has been collected from ground truth, or from ground, or from a given image, where we know that these each sample belongs to which class. And while we collect the samples, they follow some norms. The norms can be the sample should represent to a class truly, it should be well distributed, and it should be homogeneous, right? It should be homogeneous, all the samples should be homogeneous. They should be representing truly to that class only, and they should be well distributed. You can see a very layman example. When we go to a grocery shop and somebody is purchasing a one bag of rice, 1 quintal of rice, they take the samples from that 1 quintal bag from different portions. That means the samples are well distributed. Second is they are truly representing to class rice, and they are homogeneous. So all sample should look same. So these are the things we have to follow whenever we collect the samples. So let's take these methods of training data or the behavior of or training of algorithm one by one. One is supervised method. In supervised, like supervised class in a school, there is a class. So in a class, there are two components, the student and teacher. So in a class of school, information provided by the teacher. So when the information in the class is delivered by a teacher, then we can directly say that class is supervised class. So same way in the algorithm, training data is provided to calculate the algorithm parameters. So here what is happening, we are providing extra data in the form of teacher called training data, which is used to calculate algorithm parameters. Like if it is a statistical algorithm, then we can calculate statistical parameter like mean, mode, minimum, maximum, standard deviation, variance covariance parameter, and so forth. If it is a learning algorithm, then we have to train the weights, because initially weights are assumed, and with iterations we can refine the weights using the training data. With this training data, there is a label is also there. So label comes from training data, so we know the which sample belongs to which class. With the moment I say this sample belongs to this class is basically label. So classified output, so once we see in the supervised method the classified output here, on the classified output we can see they get the labels automatically, because label information is present in the training data. So this approach is simply called classification, or basically it is supervised classification. So in the output we say classified output, that means it is supervised one and there is a label. A second method is unsupervised method. Here if you take again the example of in a school, there is a class. So like there is no teacher in a class when it is unsupervised. So when the class is unsupervised, so there is no teacher in the class, so students have to learn a given topic by themselves. Themselves means they start discussing with their friends about the topic, they start exploring from internet, they start reading from book. But what happens in this unsupervised class, the student don't get confidence while reading the topic once. So they have to read this topic number of times, and then only they understand the topic. Same thing here in the context of algorithm. Initially the algorithm has to work, but we do not know the parameters of the algorithm, so these parameters are assumed. So the parameter can be mean, mode, standard deviation, so forth. So all these parameters has to be assumed. Once we get assumed value, so parameters should be simple. So now you can see once these parameters are assumed, we have to refine these parameters with respect to iteration. But here we have to take care, the parameter should be simple, like mean parameter. Mean statistical parameter can be assumed and then it can be refined easily. But if you take variance covariance, it is not so easy to refine. So algorithm which are using simple parameter can work as unsupervised mode. All algorithms cannot work unsupervised mode because their parameters sometimes are quite complicated and cannot be refined through iteration process. So this has to be, this is one difference. Second is because there is no training data, so the label is not coming from the training data. So on the output, there is no labels. And through iteration, the training parameters, what is assumed initially like mean parameter, this mean parameter is trained or trained during iteration. So through iteration, like iteration 1, 2, 3, 4, at every iteration, this mean parameter is adjusted or refined, we can say. So after the last iteration, you can see we have a more refined mean value. Initially it was assumed, because why it was assumed? Because the algorithm has to start to divide the data, but we don't have the training data, so that's why we have assumed. Now in this approach, it has some synonym word. This approach is also called clustering. So in the output we get clusters, we don't get the class because label is missing. In the output we simply say class 1, class 2, class 3, but we do not know the labels of this class. What is what class? That's why this approach is also called clustering. If it is classification, then it is supervised. When we call it this clustering and we get output as a clusters, then it is unsupervised. So unsupervised means we don't have at all training data. Third method is semi-supervised. So partially supervised method we may have, and this happens when we have a small label data, we have a small training data and large number of unlabeled data. So if we have this situation in our training data, then we can apply semi-supervised approach. So what happens initially, the algorithm parameters are calculated using small labeled data, and later it has to be defined with iterative process. So initially, whatever parameters has been calculated using limited small labeled data, that parameters are defined through iteration process, and this is called semi-supervised approach. In some of the literature you may get semi-supervised approach method. We also tried with one of the MSc student by Miss Surbhi. You can download her thesis from IIRS ITC website. If you just type Surbhi plus ITC plus IIRS plus MSc thesis, you may get, if it is there on the portal, and you can read about a semi-supervised approach. She has experimented with PCM classifier, that is a fuzzy-based classifier. A fourth learning method is called reinforced method. So this reinforced method is quite a new term in the learning or in the training of the algorithm domain. When last 5 years onwards, people start talking about deep learning, they start using the deep learning algorithms in different areas. And from there, we also got one more jargon word called reinforcement method for training. So reinforcement learning is an area of machine learning where in the absence of training data set, it is bound to learn from its experience. So that way it works. You can take some example, we can try to understand. The problem is as follows. We have an agent and a reward. So there is an agent and a reward with many hurdles in between. So there is many hurdles in between. So agent is supposed to find out the best possible path to reach the reward. So here what happens, for each action, there is a negative or positive reward, and accordingly the reward is assigned. We can see a little more in detail. The main points in reinforcement learning, one is the input should be initially state from which model will start. That is first. Output, there are many possible output as there are variety of solution to a particular problem. So the same problem can be solved by different methods. Training. So training is based upon the input. The model will return a state and the user will decide to reward or punish the model based on its output. So if we have input and output, and if we check the output, according to the output, we can decide what punishment or reward may be given to the model. So model keeps on continuous to learn based on rewards or punishment. The best solution is decided based on the maximum reward. It is a normal child. We pamper and we give chocolates when he does good thing. When he does not do good thing, then we don't do anything. But we don't give anything. We give lot of lecture to the kid. So that way the rewards or punishment is given. And in simple word, the output depends on the state of the current input, and the next input depends on the output of the previous input. So that way it is basically chain reaction. You have iterations at the new output in the next iteration dependent upon the input of the previous iteration. So that way the output is affected, and we can finally proceed through iterative process while giving the reward or punishment to the model as a numerical form. So I'm keeping the things about learning, the different learning methods we can adopt nowadays. There are 4 learning methods for machine learning or deep learning, and I goes on putting in between few lines. Always love to read these type of lines. Okay, let's go further. We'll just see to understand a little more about classifiers and method. one is supervised and second is unsupervised. So this I've already mentioned you. In the context of image, you can see for supervised, suppose we are extracting 3 classes, water, agriculture and rock. So that is a supervised one. So we are providing the samples for class water, for class agriculture and for class rock. So here we have a classifier and we are providing the training data to the classifier and the processing is happening, and here you can see the output. Each pixel has been grouped with label. So this is class A water, this is your agriculture and this is your class rock. So here in the output you can see in the supervised one you have properly pixels has been classified and there is a label given because label is coming from the training data. Same thing if you see unsupervised. So this is given in image and we don't provide anything else. We just apply unsupervised algorithm. So there is no training data. So if you see the output, the pixels are divided into clusters. Like blue is a C1 cluster, red is a C2 cluster, green is C3 cluster, and yellow is C4 cluster. So it is just dividing the pixels into clusters. While initially to start the algorithm, it assumes the parameter, and I told you the unsupervised algorithm can only work when their parameters are easy to assume and easy to refine, like mean parameter. It is easy. It is like a single digit number or a vector form, 3-4 values. So that can be initially assumed and we can refine it. But if you take like variance covariance matrix or standard deviation, you cannot easily assume them because it is complicated parameters not coming straight. There's some process followed to generate these parameters. So we cannot assume them and we cannot refine with iterations. So here in the context of image, I just talked about hard and soft classification. So you can understand how the output comes. If it is a hard case, this is a 5-band image. And here we are doing supervised or unsupervised, whatever the method you apply here. So you can see the output. Each pixel is labeled to one class. So it is a hard. Hard means the complete one pixel is a pure pixel and it belongs to totally one class. So this class 1, then this is class 2, and this is class 3, and this pixel belongs to class 4. So what are these class 1, class 2, class 3? Water, vegetation, wetland and soil. So this is a hard output, and here we get single layer output and each pixel is labeled to one class because there is no doubt all pixels are pure. Second case, same image with 5-band and it can be supervised or unsupervised. Once the pixels are mixed pixels, so this hard approach will not give you the good results. We have to go for soft classification, or previously there is a term called sub-pixel classification. Sub means within a pixel. So here in this pixel there can be class water mixed with vegetation, mixed with wetland and soil. So there can be 4 classes. So how to get it can be supervised or unsupervised algorithm we can apply. But here we are applying soft classification algorithms like nowadays any algorithm we can apply, but previously like fuzzy based can directly give you the membership values, or linear mixture model or non-linear mixture model can be applied. But today we can modify the algorithm output to save the output as a soft output. Now here you can see the output is not as a hard output, there are fraction images. So here we don't get single image, we get multiple images. There are 4 images basically because each one layer for one class: water, vegetation, wetland and soil. So here when I say image, of course it is basically like row and column. Here also this is a row and column, and it has integer numbers. Here it is also row and column, but it is not holding digital number or reflectance value or emitted value. But here in this output it is holding the membership value. Like in the first layer is for class water, second layer for vegetation, third layer for wetland, and fourth layer for soil. So what it is holding, it is holding it is storing the membership value. If you see the first pixel, the membership value for class water is 0.7. For vegetation, it is 0.1. For wetland, same first pixel, membership value is 0.1. And for soil, membership value is again 0.1. Membership value means degree of belongingness. That means this first pixel in the image by what degree belongs to class water, that is 0.7. With 0.1 it belongs to vegetation. With 0.1 again it belongs to wetland, and with 0.1 it belongs to soil. Degree of belongingness. We can see a little more in detail as a pixel level. As a hard classification, this is a pure pixel. There is only one class present in this pixel. So this pixel may belongs to class A. That means membership value is 1. And for other class, membership value is 0. Because we get only 0 or 1. But same pixel, if it is a mixed pixel, then we can apply the soft classification approach through different methods. If we apply through fuzzy method, so we may get because it is mixed pixel, there are so many classes present in this pixel, like this, maybe 3 or 4 or 5. Then class A is present with a degree of 0.1 membership value, B with 0.25, C with 0.2, D with 0.4, and E with 0.05. This membership value, if you sum, it can be 1, it can be less than 1, it can be more than 1. It depends upon which algorithm we are using. But in hard classification, if you sum, it is a 1 only, because this is 1 and rest are 0. But here the summation can be 1, summation can be less than 0, summation can be more than 0. It depends upon which algorithm we are using. We have seen at least 2 cases practically it is working. The summation is less than 1, summation is 1. I have never seen summation more than 0, but it is possible. Again, I'm telling you, everything is possible. So we have to see through which algorithm and on which data we get the degree of belongingness, which is more than 1. So all these membership values we get through membership curve. So here on the x-axis we have input data, and on the y-axis we have membership value. So for hard classification we will get only 2 values, either 0 or 1. And for soft classification we get a continuous value from 0 to 1. So advantage of soft classification, there are 2 things. There is no relative standing. The relative standing is maintained, right? If the element belongs to a class with 0.5, it belongs with 0.5 only. The second element belongs to same class, but with higher degree, maybe 0.8. So there is relative standing. But in the case of hard classification, 2 pixels may belong to same class. Practically they have different degree of belongingness, but hard classification says both have same degree of belongingness. I will give you one example. Like in a real life in the university, when we get grades, it is a hard classification. The condition is for A+. The A+ means the mark should be 75 or more than 75. So the person who got 99, he got A++. The person who got 75, he got A++. So both the relative standing is lost. The 75% marks student is standing with the 99% marks student. So there is no relative standing in the hard classification, and there is local stress. The third student who got 74.000009 or 74.99999, he cannot get A++ because he does not have marks 75 equal to 75 or more than 75. So there is local stress at 75, and out of 3 students, the student who got marks 74.99, he has a highly stressed A. So there is a local stress at 75, and there is no relative standing. But in the fuzzy domain, like in the class, if you say percentage, the student got 74, fine, 74.99, second got 75, and third got 99. So 75% is not standing with 95% marks, and 74.99 is more or less equivalent to 75, because we are not giving the grades system. So that way the relative standing is maintained in the soft approach or in the fuzzy domain, plus there is no local stress. So these are 2 advantages in the fuzzy domain. We can see output just as a glimpses in the context of image. This is one Ponta image of list 4. and we have tried the 4 bands. The black color indicates to be tending to 0 membership value, and the white indicates tending to 1. So here you can see in the first output the barren lands with the white small patches where the membership value is tending to 1. We can see agriculture patches, membership value tending to 1. We can see dense forest, and wherever it is white, the membership value is 1. Wherever it is not white, gray or black, membership value is low. And this gives you realistic output on the ground, because you can see on the ground the forest is not exactly dense forest. There are partially small grasslands, or there is some degradation of the forest. That actual information we can indicate through membership value. Same way for the water body, there is Asan river here, this is Yamuna river, and this is Gir river. So all are joining to Yamuna, and this is Asan barrage, which is quite deep, which has more membership value tending to 1. Here water is shallow, so somewhere it is deep and somewhere it is shallow. Wherever it is shallow, the membership value is not tending to 1. So that actual representation on the ground we can see through degree of belongingness, that is membership value. So this gives you real true representation with respect to ground. So there is a statement also, everything on the ground is fuzzy. So there is nothing hard or crisp set theory. Crisp set theory is a subset of fuzzy set theory. Everything is fuzzy in this life. We can see some of the further aspects or issues what we encounter specifically for remote sensing images, and same type of issues we can see in other images while handling the. So here I'm talking about different aspects while handling or processing the remote sensing images. One is mixed pixel. So here you can see these pixels are totally grasslands. These 2 pixels are water body. What the label I should give to these pixels? Somewhere in this pixel there is grassland and water. 2 classes are mixing due to the boundary, because they are representing the boundary. So we can handle these mixed pixels through fuzzy domain, because fuzziness can handle the incompleteness. There is a vagueness, uncertainty in these pixels, which can be handled very nicely through fuzzy logic. Second thing, here you can see in this image the red dots are the noisy pixels. How to handle these noisy pixels? So here we have tried to handle these noisy pixels through MRF, Markov random field, which basically incorporates the local correlation method with the neighbor pixels. Also, we have tried with local convolution method through window approach to remove the noise. Then there can be always isolated pixels, like 1 pixel of water body is bounded with a forest area. If I'm preparing a map from a remote sensing image at 1:20,000, there is no meaning to show these isolated pixels, because at 1:20,000 I cannot show this individual pixel, but this pixel will come in on the output as a water body. How to eliminate? Again, we can remove it through Markov random field approach or through local convolution method. So through these 2 methods we have tried to remove the noisy pixels or isolated pixels. So this is one of the output and case of Markov random field. It's 2 models we have applied, and here I'm showing you a case study of water body. So this is the input image, a LIS4 image. This is a dam and small water bodies near to the dam. We can see 3 water bodies. And the first model through a Markov random field as a smoothing prior, when we have applied, it does smoothing of the pixel. It incorporates the neighbor pixel, but this also gives a smoothing effect, and that's why you can see there were 3 water bodies. This has been vanished. This water body is not coming fully, and this is also not coming fully as it is, because these boundaries has been dissolved. Second model through MRF we have applied through discontinuity adaptive prior DA model, and here you can see these water bodies are more or less preserved, and the boundaries are also preserved, so they're not so much smooth. Second mode of handling the noise we have tried through local convolution method or local information method. That means adding the neighbor pixels. So what we have experimented, this is the input image from central image, and this is the output for wheat class without noise, assuming this image is noise free. But here we have tried 1% noise intentionally, and then we have applied the classification approach for the wheat class. And here you can see the 1% soil and paper noise has been handled very nicely. This output is not much affected due to noise. Later we have increased this noise to be of up to 5%, and again we have seen the output. So up to 5% we were able to handle the noise through local convolution method. Another method we can see between classes. Generally, the classes are linearly separable, but in some cases there is non-linear separation here. Here in this case, it is a non-linear separation between two classes. So any of the classifier, if I apply, they cannot handle this non-linearity boundary. So what we have to do, mathematically, we have to apply some kernel in that algorithm. What it does, it takes this data and make to higher dimensionality and make the data to be linearly separable. So it gives the linear decision boundary, and after that, if we apply any of the classifier, we can achieve much better accuracy. So the kernel is the method to linearize the class separations, and what it does, it takes the data to high dimensionality, and there you can see the data has the linear separation between two or more than two classes. One more problem we can see in the remote sensing, the spectral overlap, specifically when we are mapping a higher level of classification. Like the first level of classification can be just a thematic map, water body, forest, agriculture, settlement. But within agriculture, the agriculture field having crops, and in that crops we are trying to discriminate where is wheat and where is mustard, because both this wheat and mustard are the rabi crop grown in the same time. If you see these fields, they appear more or less same reflectance, so they have spectral overlap. The question comes how to handle when we go for higher level of classification. Within wheat, we want to map the diseased wheat fields, or we want to separate wheat with mustard or another crop. So in that case, we have to use temporal information from the remote sensing images. Nowadays, from Sentinel 2A and 2B, if you take the data from both the satellites 2A and 2B, you may get easily around 5 to 10 days data. Ideally, every 5 days, you can get the one image of the same area. And if you incorporate this temporal information, you can easily separate the overlap between classes. So here you can see a lot of overlap, spectral overlap between classes. So here you can see to incorporate the temporal information. If you see the specific crop, how it goes, how the field changes. Initially it is fallow. After some time, there's a very small young tree, young plant. Then it is growing further. Then it is further growing, and it is reaching to the flowering stage. Then you can see proper flowering, and with milking in the seeds. And then in the last week, the tree goes, that plant goes to the harvesting stage. So if you see the chlorophyll content on the same field, it is following this more or less this curve, this graph. So you can see this graph is representing the phenology of that crop, and through temporal images, we can incorporate this phenology. So within agriculture fields, mapping specific crop at level 2 or level 3 classification is possible when we incorporate this temporal information, and that can handle the spectral overlap between different existing crops in a given area. So this also provides basically phenological information from temporal images. Is very, very important when you want to discriminate and map the classes at level 2 or level 3. So level 2, level 3, I have explained. Level 1 agriculture field with crop. Level 2 is within crop. What different crops are there? Wheat crop is one, mustard crop is one, second can be, third can be fodder. Within wheat, you want to go for level 4 or level 3 or level 4 classification. What type of that wheat is, its variety, it is sown early or before or late or mid sowing. So all these level 3, level 4 classification you can do if you have temporal information through temporal remote sensing images. So this is all about, just I talked about in this first lecture. For today's lecture, this is basically fourth one. Starting with training concepts, and then issues, what different issues we encounter, how we can handle these issues. And some of the issues are very, very important. I will give you the next lecture, and there you can see the role of temporal data, how that temporal information is important for mapping specific class that can be in agriculture or forest or urban or your geoscience post landslide studies. So thank you all for this first lecture, today's one, and